welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about the models which represents tumor growth. So let us see what is a tumor. So basically a tumor is a mass or group of abnormal cells that forms in the body, and that takes place because of some problem with the DNA structure whose reason actually is not known. So, as you can see, the cells in the video, they are growing so fast. So, that is what the tumor is, and they try to connect with the blood vessels. So, either they generate it or they try to connect it with the blood vessels, through which they send the malignant tumor cell and which affects the other parts of the body. So, that is how a tumor works. However, not all the tumors are malignant, that is cancerous. Some of them are benign, and the word is benign and not cancerous. So, scientists have used this mathematical modeling to assess the growth of the tumor, and we have many mathematical functions that gives somewhat good results, and they can represent the growth of a tumor. So, to start with, we have this linear tumor growth model. So, the first equation here, it says dt dt equal to k, where your capital T is the tumor and this is the time. So, rate of change of time is a constant, and we say it is a linear tumor growth. Obviously, they are quite easy to solve, and if you just want to solve, it will be some t equal to k times t plus some constant. And since this is a linear equation, the tumor growth is called a linear. As you can see, it is a straight line, and hence the graph which you get is also a straight line. So, the tumor grows like this. Now, sometimes it happens that the cells, they also kills themselves. So, it is called the natural decay of the cells or the natural death of the cells. In that particular case, you have the growth constant, and this is the natural decay or death of the cell, and hence we get something like this. In that particular case, you have the curve like this, and if you want to generate this curve with the help of Microsoft Excel, for this case the value of this k is equal to 2. For this case the value of k is again 2, but d is equal to 0.01. So, if you plug these values in this differential equation and solve it, you will going to get this kind of curves. The question is then why we are having so many differential equations to represent the tumor growth. That is because the tumor growth varies from person to person, and there are so many kinds of tumor, and it has been noticed that, say, in case of brain tumor, this particular kind of function matches, and in case of, say, tumor in the lungs, this particular kind of function matches the data, and hence we have several kinds of growth as far as this tumor growth is concerned. So, our second kind will be the exponential tumor growth, and the exponential tumor growth is dt dt is equal to kt, and that is because if you solve this, dt by t equal to k dt, if I integrate, that is ln t is equal to kt plus some constant, and you can see that t can be expressed as exponential of kt plus constant. So, that is why it is called the exponential tumor growth model, and with the same logic I say that there is some natural death of tumor cells, and hence this minus dt comes here, but again I can just take k minus d times t, replace this by certain constant, and you get the solution same as like this. So, this is the two graphs that you will get for tumor growth model, and in this particular case we take the value of k to be 0.1 and d as 0.01. This particular thing also known as shrinkage. But it's easy way to remember that this is caused by the natural death of the tumor cells. And if you notice and compare both the graphs, you will see that here the growth is a bit sharp, whereas here it is a bit flat and then going again up. Both are exponential, but due to this component, the growth of the tumor cell is somewhat a bit less because it's given a negative sign, whereas this grows totally exponentially without any shrinkage or very natural death of the cell. The next one is the logistic and Gompertzian tumor growth model. We have done the logistic and Gompertzian growth. So, once again, if we recall those, the rate of change of tumor is equal to some kt into 1 minus t by t max, where this k is called intrinsic growth rate and this T max is called the carrying capacity. So, the carrying capacity is the maximum resources that the environment can sustain. So, in this particular case, the tumor gets its resources from the body. So, the maximum tumor cell that your body can sustain, and this k is the growth rate. If you plot them with the values k equal to 0.1 and d equal to 0.01 and your T max is equal to 120, you will be able to generate this figure. So, this is your logistic growth. In the Gompertzian growth, you have the equation of the form the rate of change of tumor is equal to k times t into log of T max by t. So, in this k is again the intrinsic growth rate and this T max is the carrying capacity, which we have explained before. With the same numerical values, you will be able to plot a graph like this. Now, again the question is where you will use the logistic growth and where you will use the Gompertz growth. So, in tumor models you get the data. The data is that with respect to time how the tumor is growing directly from the patients. We will be able to measure that, and once you measure that, you are going to plot those datas and then try to fit one of these functions in that particular data. And the function which matches most with the data is the function that we take to represent that particular kind of tumor. So, that is why we are learning so many forms of tumor growths, so that for a particular tumor we just able to see that which particular functions actually fits the data. Obviously, you can do the equilibrium points and stability analysis of this all these models, which I just keep them for you, as we have done lots on this single differential equations. So, here only we discuss about the different growth models of tumor. So, the next one is the combined exponential and linear tumor growth model. So, here it is the rate of change is given by some lambda 0 t divided by 1 by lambda 0 by lambda 1 t to the power 20, this whole to the power 1 by 20. So, obvious question is what is your lambda 0, what is your lambda 1. So, this lambda 0 is the rate that represents this exponential growth, and lambda 1 is the rate that gives the linear growth. Now the question is how this 20 suddenly pop up in this particular function. Well, it didn't start with 20, it can start with some n, but then scientists have taken various values of n and ultimately zeroed it down to 20 because they saw that the kind of graph they are getting, it matches a particular kind of data, and 20 gives is a very good match for those kinds of data. So, that is why this particular function has been discovered, and this proved to be quite a good fit for some kind of tumor growth model. There is another model which is called Bertalanffy model. In this particular model, the volume of the tumor is measured, and that follows this particular equation, v to the power 2/3 minus bv. So, A is again the intrinsic growth rate, and B is called the rate of anti-angiogenic process. Now, what is angiogenic process? So, what happens is, as you have seen in the video, that this aim of this tumor to connect them with the blood vessels, either they grow of their own, which is called the angiogenesis, or they try to the cells try to go and connect with the blood vessels of the body, so that they can circulate all the malignant tumor cells throughout the body, and that is how a person gets infected very fast. So, antigenic process means that there will be some drugs which will stop the growth of these blood vessels. So, this particular B is take care of that. It kills, or it does not allow the tumor to grow by its anti-angiogenic property. So, this is one kind of tumor growth model and Bertalanffy model. Now, let us take what happens with treatment. So, here you see that it is growing exponentially, and we have minus some k1t. So, due to drug effect, whatever it is killing the tumor at the rate k1. So, in this particular case, and the one we have done where I have shown the model is something like kt minus some dt, this was the natural death. But here, due to some drug, this particular tumor is getting eradicated or getting killed. This is exponential. And so, your curve, it starts with some initial value of the tumor, it is growing with due to this term, but the drug is killing the tumor cells, and hence it is going down and ultimately go down to 0. Now, this is an exposure dependent treatment effect. Now, what does it mean? That again it is doing exponential growth, and this exposure is due to drugs. So, what does this exposure means is that there is a time interval or the time span during which your drug is going to work, and various doses of drugs are going to be applied inside the body of the person suffering from this tumor. So, this exposure is due to the drugs, and which helps in killing the tumor cells at a rate k1. So, that is why minus k1 times some exposure, which is going to be a function, which can be a function of time, and generally people use what is called Hill's function. I am not going into that, it is a very complicated function not needed for this particular course, it is kind of research level thing, But anyway, the idea is that you can use a functional form of time to ensure that the drugs are applied inside the body and the people get cured. So, this kind of model is also applicable. Special form of exposure is that okay, you have a function, then you multiply it again with respect to some exponential factor of time, that with time the effect of drug slowly goes off. So, here it is an exposure dependent treatment, but with resistance. So, what happens is that there is a person suffering from tumor, he is having an exponential growth of tumor, and then the drug is given, but then with time that the effect or efficacy of the drugs that goes out, and due to which you see that that there is a tumor which is going down, but the moment the effect of the drugs goes up, the tumor also relapse. And this is very known case scenario which happens in many patients. So, with that we come across a lot of models which gives you an idea of the growth of the tumor cells and the corresponding effect of drugs on the tumor cells. Before going to the numerical solution, we just check the equilibrium points and the stability of two such growth models. You have to do with all the models. I just take the example of two of them. So, to start with, we take the logistic growth, where we have denoted the equation as dt, where capital T is the tumor, K is the intrinsic growth rate, and T max is the carrying capacity. So, to find the equilibrium point, we put this equal to 0 and we get Kt 1 minus T by T max equal to 0. And if we solve this, I will get T equal to 0 and T equal to T max. Now, to find the stability, you take some Ft is equal to Kt 1 minus T by T max. I find what is F dash T, which will be K minus 2 Kt divided by T max. Now, at T equal to 0, F dash 0 is equal to K, because this goes to 0, which is positive, which implies the system is unstable about the equilibrium point T equal to 0. And if you find F dash T max, so this will be K minus K T max divided by T max. So, this cancels and this is K minus 2K, which is minus K, and which is less than 0 because K is positive. So, this implies that T equal to T max is asymptotically stable about the equilibrium point. T equal to T max. So, the system is asymptotically stable about the equilibrium point T equal to T max. So, this is the equilibrium point and the stability analysis for the logistic growth. Let us take one more where we have taken Gompertzian growth. So, there the equation with which we represent the growth is Kt log of T max divided by T. And if you want to find the equilibrium point, I have to put this equal to 0, and this will give me T equal to 0 and ln T max by T equal to 0. And the base of this ln is E, so T by T max, T max by T is equal to e to the power 0, which is 1, and this gives T equal to T max. Now I can write this dt as Kt ln T max minus ln T, and let us take that to be some Gt. So your G dash T will be given as K times ln T max by T plus Kt into minus 1 by T. This T cancels. So K ln T max by T minus K. So if you want to check what is G dash 0, you will see that your ln T max by T is undefined. And this implies that here T equal to 0 is a singular point, and we cannot conduct the stability analysis for this point T equal to 0. So we stick to only T equal to T max. And you see that G dash T is equal to K ln T max divided by T max minus K. This is log 1, which is 0, and you are left with minus K, which is less than 0 because K is positive. And hence, here also the system is asymptotically stable about the equilibrium point T equal to T max. Now let us see how you will generate the numerical solutions with Microsoft Excel. So I already have filled it up because there are so many equations and it will be so time consuming. So the first is the linear one, this two. Then we have the exponential one, this and this. Then we have the logistic one and the Gompertzian one. I have also this equation which depends on volume. So basically 1, 2, 3, 4, 5, 6, 7. So here also 1, 2, 3, 4, 5, 6 and this 7. The one which I left is this one, which I will just do it now. So this is, so we use the Euler's method, which is this one, and this is equal to T0, which is this value, plus H, which I have taken to be 1, and it is a constant value, multiplied by this particular function lambda 0, which is 0.1, multiplied by T0, which is this value, and this whole thing has to be divided by 1 plus, again a bracket open, so lambda 0, this one, divided by lambda 1 which is this one. Again, this is a constant, lambda 0 divided by lambda 1. This goes in a bracket multiplied by t, which is t0, and then whole thing goes to the power 20. And then this whole thing goes towards 1 by 20. So, from 1 again till this one to the power 1 by 20. Okay, let's see. So, we get here 5.5, and then we drag this till say 50 values, and I get these values. Now, what we do is we plot all of them in the same graph. So, all the 50 values, I go to insert, I go to this, and I plot this. So, now the question is what we get with this. So, you can solve them individually and you can get the individual graph, but what I want here is that I want to compare this with various models. So, the idea is that there are so many functions and so many dynamics of the functions. Now, which one to follow? So, what the scientists do is that they get data for a particular kind of tumor. So, whether it can be a tumor of the brain, or whether it can be the tumor of the lungs, or whether it can be the tumor in the pancreas. So, all these sort of data, once they plot it, they look for a function that will match those data. And so, we have so many kinds of function which the researchers have seen that they give a match to these particular tumor growth data. And that is why we are learning here so many functional mathematical form. So, it depends that what kind of data you get, and then you try all these equations, all these kinds of growth to match that particular kind of data and see that which particular function match that particular tumor growth. So, with that we come to the end of this particular lecture where we have discussed various forms of tumor growth. In the next lecture, we will be talking about some more interesting models. Till then, bye bye.